quantum gravity and the rejection of the multiverse. In the depths of our cosmos, a profound question has emerged, one that challenges our understanding of reality itself. Is our universe the unique, self-contained cosmos we experience? Or is it merely one bubble in an endless sea of universes? Today, we embark on an exploration of quantum gravity and examine how cutting-edge theories are pushing back against the idea of an infinite multiverse. Historical foundations. The idea of multiple universes isn't entirely new. In 1957, Hugh Everett III introduced the many worlds interpretation of quantum mechanics, suggesting that every quantum event births alternate outcomes, a conceptual branching of reality. While Everett's vision dealt with quantum events, the cosmological multiverse found its roots in the theory of cosmic inflation. Developed in the early 1980s by Alan Guth and later refined by Paul Steinhardt, cosmic inflation proposed a brief epoch of exponential expansion in the early universe. As space expanded at an unfathomable rate, tiny quantum fluctuations seeded the formation of distinct bubble universes. Each bubble could, in principle, host its own laws of physics. But the story deepens with the emergence of string theory in the 1980s and 1990s. Initially hailed as a potential theory of everything, string theory soon revealed an astonishing landscape, a potential 10 to the 500 different vacuum states. Rather than prescribing a single set of physical laws, it suggested a vast ensemble of possibilities, a natural breeding ground for the multiverse hypothesis. As brilliant minds grappled with these ideas, a crucial tension emerged. While a multiverse could account for the fine-tuning of our own universe, it also risked placing science on an untestable pedestal. Could a theory that predicts countless unseen universes be empirically validated? Or is it a seductive mathematical mirage? At its core, the debate revolves around two pillars of modern physics: cosmic inflation and quantum gravity. The inflationary model tells us that the early universe expanded exponentially, ironing out irregularities and setting the stage for the cosmos we observe today. Yet, quantum fluctuations during this phase could trigger endless pockets of inflation, each one a candidate for a separate universe. Simultaneously, physicists have sought a quantum theory of gravity, a framework that unifies Einstein's general relativity with quantum mechanics. General relativity describes gravity as the curvature of spacetime, elegantly formulated by Einstein's field equations. However, when we probe the universe at the tiniest scales or near singularities, the predictions of general relativity break down. Efforts to reconcile these regimes led to the Wheeler-DeWitt equation, an attempt to describe the entire universe with a single, timeless wave function. Complementing this, string theory emerged, replacing point particles with vibrating strings. This theory not only offers a way to quantize gravity, but also introduces the holographic principle, a revolutionary idea suggesting that all the information within a volume of space might be encoded on its boundary. These advancements hint at a fascinating possibility. If the mathematics of quantum gravity is correct, the overwhelming diversity predicted by eternal inflation might be dramatically curtailed. Stephen Hawking, in his final work with Thomas Hertog, used such ideas to argue that a proper quantum treatment yields a finite set of possibilities, a universe that is smooth and globally finite, rather than an unbounded, chaotic multiverse. In this view, the mathematical structures, whether through holographic bounds or discrete spacetime in loop quantum gravity, may enforce limitations. Instead of allowing every conceivable outcome, nature might only permit a narrow band of possibilities, one that is directly connected to the conditions we observe. At the heart of this debate stand towering figures whose work has shaped our understanding of the cosmos. Stephen Hawking, whose legacy is inseparable from black holes and the origins of the universe, became increasingly skeptical of an endless multiverse. Collaborating with Thomas Hertog, Hawking employed the holographic principle to tame eternal inflation, suggesting that our universe is not a drop in an infinite sea, but rather a well-defined outcome of quantum processes. Not all agree with this approach. Roger Penrose, for example, has championed an alternative known as Conformal Cyclic Cosmology, or CCC. In his bold vision, the end of one universe smoothly becomes the beginning of another, a cycle where the cosmos is reborn over infinite eons without invoking a sprawling multiverse. Meanwhile, Paul Steinhardt, one of the original architects of inflation, now warns that an over-reliance on the multiverse undermines scientific predictability. He, alongside collaborators, has developed cyclic and ekpyrotic models, where our universe undergoes periodic phases of contraction and expansion, resetting its conditions with each cycle. Lee Smolin offers yet another perspective with his idea of cosmological natural selection. In this scenario, universes reproduce through black hole formation, and natural selection favors those with physical laws conducive to black hole production. While Smolin's theory still entertains multiple universes, it replaces randomness with an evolutionary mechanism, a process that might eventually reveal why our universe is so finely tuned for life. Each of these ideas, be it Hawking's finite ensemble, Penrose's cyclic cosmos, or Steinhardt's cyclic models, presents a challenge to the traditional multiverse narrative. Rather than an infinite proliferation of disconnected bubble universes, these approaches suggest that the cosmos might be far more orderly, with deep underlying principles that enforce a unique or limited set of outcomes. These alternative models carry profound implications. If the cosmos is indeed constrained by the principles of quantum gravity, then the seeming fine-tuning of our universe, its precise physical constants and laws, might be a natural consequence of deep, yet-to-be-discovered principles rather than mere anthropic luck. But how do we decide between these grand theories? The challenge lies in the fact that other universes, if they exist, are inherently beyond our direct observation, yet our own universe serves as a laboratory for cosmic clues. Observations of the cosmic microwave background have been a treasure trove of information. Satellites such as COBE, WMAP, and Planck have confirmed that the early universe was incredibly uniform, a hallmark of inflation. Yet scientists have scoured this ancient light for subtle anomalies that might signal a collision with another bubble universe. So far, these searches have yielded no convincing evidence. Instead, the data reinforce the picture of a remarkably smooth cosmos. Meanwhile, researchers are turning to the hunt for primordial gravitational waves, ripples in the fabric of space-time predicted by inflationary theory. Experiments like BICEP Keck and upcoming projects such as CMB Stage 4 aim to detect these elusive signals. A definitive detection would not only cement the inflationary paradigm, but also constrain the energy scale at which inflation occurred, indirectly informing the debate over whether a multiverse naturally follows. Other efforts involve large-scale structure surveys that map the distribution of galaxies, as well as experiments at particle colliders like the LHC, which search for signatures of extra dimensions or supersymmetry, both ingredients in many multiverse scenarios. So far, the evidence is ambiguous. Our current data support a universe that obeys familiar laws, while the exotic fingerprints of a sprawling multiverse remain, at best, hints in a cosmic tapestry. Even in the realm of quantum gravity, experiments are beginning to test its subtle predictions. Researchers look for tiny deviations in the propagation of light or gravitational waves that could signal the graininess of space-time itself. While these experiments have yet to yield definitive results, they point to a future where quantum gravity might transition from theory to observable reality. In the interplay between observation and theory, the ultimate fate of the multiverse hypothesis remains uncertain. Each new dataset sharpens our understanding, offering a chance to either bolster the case for a finite, regulated cosmos, or leave us with the tantalizing possibility of realms beyond our own. Beyond the mathematics and observations, these debates force us to confront profound philosophical questions. What does it mean for a theory to be scientific? At its core, science demands testability and falsifiability. Critics of the multiverse argue that if other universes are forever beyond our reach, the theory risks drifting into the realm of metaphysics, a beautiful idea without empirical backbone. Yet defenders counter that our very best theories, from quantum mechanics to general relativity, were once as inaccessible as the multiverse appears today. They assert that if a theory naturally predicts a multiverse as an inevitable consequence, just as inflation naturally predicts the smoothness of our cosmos, then the multiverse should be taken seriously, even if indirectly. This debate touches on Occam's razor, too. Is it more parsimonious to assume one unique universe governed by unifying laws? Or must we accept an endless proliferation of possibilities to explain the fine-tuning of constants and the structure of reality? And if our universe is but one of many, what does that mean for our place in the cosmos? Perhaps most importantly, these questions challenge us to redefine what counts as an explanation. If the universe's laws and constants arise from an underlying quantum gravitational framework that forces only a narrow range of possibilities, then what seems like an act of cosmic luck might in fact be inevitable. In this view, our universe is not an arbitrary accident, but the necessary outcome of deep, fundamental principles. What is a scientific explanation? While the debate remains unresolved, it has undeniably spurred a re-examination of our methods and the very scope of scientific inquiry. It's a vibrant reminder that even the most abstract questions about the cosmos can inspire real, tangible progress in how we understand our universe. Our journey through the realms of quantum gravity and the rejection of an infinite multiverse has taken us from the earliest ideas in quantum mechanics to today's cutting-edge research. While theories continue to evolve, one thing remains clear. The quest to understand the ultimate nature of reality is as vibrant as ever. Will quantum gravity reveal that our universe is a uniquely defined outcome of fundamental laws? Or does the mysterious possibility of a multiverse hold secrets yet to be uncovered? The answer may lie in future observations, theoretical breakthroughs, or perhaps entirely new ideas we have yet to imagine. I invite you to join the conversation. What do you think? Is our cosmos a singular masterpiece, or merely one panel in an endless cosmic mosaic? Share your thoughts in the comments below. And if you enjoyed this deep dive, please like, subscribe, and hit the bell icon so you won't miss our next exploration into the mysteries of the universe. Subscribe for more deep dives, comment below. What's your take on the multiverse? Thanks for watching. Until next time, keep looking up.